Hello everyone, welcome to my channel Physics for Engineers. I am Dr. Tirumala Gurugubelli, Associate Professor and Head, Department of Basic Sciences, School of Sciences and Humanities, SR University, Warangal, Telangana, India. In this lecture, we are going to discuss about the classification of semiconductors, particularly the intrinsic semiconductors, the current flow in intrinsic semiconductors. As already we discussed in the previous lecture, the semiconductors are classified into two major groups. One is intrinsic semiconductors and other one is extrinsic semiconductors. Intrinsic semiconductors are pure semiconductors which are available in nature. So the basic examples of intrinsic semiconductors are silicon and germanium. Whereas coming to the extrinsic semiconductors, there is also known as doped semiconductors. So based on the doping element, the extrinsic semiconductors are classified into two groups. One is N-type semiconductor, another one is P-type semiconductor. N-type semiconductors are made by doping a pentavalent impurity atoms like phosphorus, arsenic, and the P-type semiconductors are made up of doping with trivalent impurity atoms like aluminum, gallium, etc. In N-type semiconductor, the majority of charge carriers are electrons and minority charge carriers are holes. Whereas in P-type semiconductor, the majority charge carriers are holes and the minority charge carriers are electrons. If you see the intrinsic semiconductors, the number of charge carriers, number of electrons and number of holes are equal. Let us discuss about the intrinsic semiconductors in more detail. An intrinsic semiconductor is a perfectly pure semiconductor without any added impurities. The most common intrinsic semiconductors are pure silicon and pure germanium. In silicon, every atom shares its 4 valency electrons with neighboring atoms through covalent bonding. At absolute zero temperature, all electrons remains tightly bound in these covalent bonds. Consequently, there are no free charged carriers available for conduction. That's why the intrinsic silicon behaves like an insulator at absolute 0 Kelvin. However, at room temperature, the thermal energy becomes available. This thermal energy can break some of the covalent bonds and releases some of the electrons. Whenever an electron leaves a bond, it creates two charge carriers simultaneously. One is the electron is relieving from the bonding, where the electron is leaving from the particular place where the vacant position will be created. That vacant position is nothing but hole. So one free electron and one hole will create simultaneously when the bonding is breaks down. Since every generated electron is accomplished by one hole, the concentration remains equal. This is why intrinsic semiconductors satisfy the basic law, the number of electrons is always equal to the number of holes in intrinsic semiconductors. Because only a limited number of electrons are thermally excited, intrinsic semiconductors exhibit relatively low conductivity. The understanding of intrinsic semiconductors is essential because they provides the fundamental foundation for understanding all doped semiconductor devices. In particular, the electronics, pure semiconductors are rarely used directly because their conductivity is too low for the most of the applications. Therefore, the engineers introduced the impurities to create extrinsic semiconductors with higher electrical conductivity. Let us carefully observe what happens inside an intrinsic semiconductor. If you see the crystal structure of a silicon, the crystal lattice, every silicon atom forms 4 covalent bonds with the neighboring atoms. Those bonds creates a stable structure at low temperatures. At low temperatures, the electrons remains tightly bound with these covalent bonds. As temperature increases, the thermal vibrations become stronger. Eventually, some of the electrons gains sufficient energy to break the bonding and free from their bondings. Once an electron released, it will move into the conduction band and become available for electrical conduction, that we called free electron. The missing electron leaves behind an empty position known as hole. A hole is a positive charge carrier. It is not a physical particle. Instead, it represents the absence of an electron. However, the hole behaves like positively charged particle because neighboring electrons continuously moves to fill the vacancy. So whenever the bonding breaks, one electron is leaving from its original position by creating a hole. That hole will attract the another electron from the nearest neighboring atom. So the hole will shift to that position. So it will be continuous. The electron and hole will continuously move to create the free charge carriers. As electrons moves from one bond to another, the holes appears to move in the opposite direction. This motion contributes to electrical conduction. Thus, in intrinsic semiconductors, both electrons and holes participate in current transport. This dual carrier conduction is one of the distinguished features of semiconductors. Unlike metals, where only electrons carry the current, in semiconductors, both electrons and holes will contribute to the electrical conductivity. This concept becomes extremely important when we study p-n junction diode and transistor operations in the latter part of this course. We can see the illustration of generation of electrons and hole pairs, how the electrons and holes are generating. Whenever the sufficient thermal energy is supplied to the semiconductor, the covalent bond breaks. The released electron enters to the conduction band and becomes free charge carrier. Simultaneously, a hole is created in the valency band. The electron hole pair is always generated together. This is a fundamental principle in semiconductor physics. The induced electron hole pair will contribute to the electrical conductivity in semiconductors. We cannot generate a free electron without creating the corresponding hole. Simultaneously, when a free electron recombines with a hole, both charge carriers will disappear simultaneously. This is the charge carrier recombination is the very important and key phenomena in semiconductor physics. Particularly in luminescent materials like LEDs, the charge recombination plays a crucial role. So in the process of recombination, the two important processes continuously occurs inside the semiconductor. One is generation, second one is recombination. At thermally equilibrium condition, the generation rate equals to the recombination rate. As temperature increases, the generation rate increases significantly. Consequently, the more charge carriers becomes available and conduction increases. This explains why semiconductors exhibit a negative coefficient of temperature of resistance. The concept of electron hole pair generation is also crucial for understanding the solar cells. When sunlight strikes a solar cell, photons generate electron hole pairs. The separation of these carriers produces electrical energy. Thus, the same physical principle responsible for intrinsic conduction also. This also enables the renewable energy technologies. Now, let us understand how current flow takes place in intrinsic semiconductors. Suppose a voltage is applied across a semiconductor crystal. The electric field created by the applied voltage exerts force on the charge carriers. Electrons are negatively charged. Therefore, they move towards the positive terminal. Holes have a positive charge carriers. Consequently, they move towards the negative terminal. You can see how the electrons and holes are moving towards the positive and negative terminals like conduction band and valency band. Although the electrons and holes moves in opposite directions, both contributes to the current flow in the same overall direction. This is an important concept that often confuse the students. Remember, electron motion contributes to current, hole motion contributes to current. The total current is sum of electron current and hole current. In intrinsic semiconductors, the electron current is equal to the hole current. So approximately, because electrons and holes concentration are equal. However, electron mobility is generally higher than the hole mobility. Therefore, the electrons often contribute slightly more to the conduction than holes. This mechanism of current flow forms the basis of semiconductor device operation. Every diode, transistor, solar cell, and the integrated circuit depends on the controlled movement of electrons and holes. You can see here how the current flow takes place in intrinsic semiconductors. This diagram visually explains the movement of electrons and holes within the intrinsic semiconductor. Note that when an electron moves away from its original bond, the hole is left behind. A neighboring electron can move to fill this vacancy. So the hole will move to that electron position. This process repeatedly happens throughout the crystal lattice. Holes appears to move through the material, although the holes are not physical particles. Their movement can be treated mathematically as the movement of positive charges. This greatly simplifies the semiconductors analysis. Think of a row of empty seats in a classroom. If students continuously shift to occupy the nearest empty seat, the empty seats appears to be moved along the row. Similarly, the holes moves because the electrons continuously fill adjacent vacancies. Here the electrons are moving to the vacant position so that the hole is moving to the electron position in the back side. That's why it appears like the holes are moving backside in the opposite direction. This analogy helps to understand why hole motion contributes to the current flow. The simultaneous movement of electrons and holes enables intrinsic semiconductors to conduct electricity despite being composed of natural atoms. Understanding this visualization is essential before studying doped semiconductors and p-n junction diode devices. Before moving to the extrinsic semiconductors, let us summarize the key characteristics of intrinsic semiconductor. An intrinsic semiconductor is chemically pure, free from intentional impurities, electrically neutral. At room temperature, the thermal energy generates electron-hole pairs. The number of free electrons is equal to the number of holes. Therefore, we can say the number of charge carriers, the number of electrons is equal to number of holes in intrinsic semiconductors. The conductivity of intrinsic semiconductors depends primarily on the temperature. As the temperature increases, more electron hole pairs are generated. The carrier concentration increases so that the conductivity also increases and the resistance or resistivity will be decreases. Although the intrinsic semiconductors helps us to understand the fundamental semiconductor behavior and their conductivity is relatively low. This limitation restricts their direct use in practical electronic applications. To overcome this limitation, the engineers introduced the controlled impurities through doping to control the charge carrier density and mobility of charge carriers in the semiconductors. Doping dramatically increases carrier concentration and conductivity. This leads to the formation of N-type and P-type semiconductors. These doped materials form a building blocks of diodes, transistors, integrated circuits, microprocessors, LEDs, and solar cells. Therefore, the intrinsic semiconductors serves as the foundation upon which modern electronics is built. In the next section, we will explore how doping transforms the pure semiconductors into highly conductive and technologically useful semiconductor materials. Previous slides, we learned about intrinsic semiconductors, which are pure form of silicon and germanium. We saw that the materials can conduct electricity because thermal energy generates the electron hole pairs. However, we also discovered that the conductivity of intrinsic semiconductors is relatively low. Now, let me ask a simple question to you. Imagine you are designing a smartphone processor or a laptop motherboard or a communication device, anything. Would a material with very low conductivity be sufficient for the efficient operation? The answer is absolutely no. Engineers need materials whose electrical properties can be precisely controlled. This requirement leads to one of the most revolutionary concept in semiconductor technology known as doping, which gives rise to the development of extrinsic semiconductors. So, what exactly is the extrinsic semiconductor? I can say that an extrinsic semiconductor is a semiconductor whose electrical conductivity has been intentionally modified by adding a very small amount of impurities atoms into the pure semiconductor crystal. The word extrinsic means that its properties are influenced by an external factor. In this case, the external factor is the impurity atom that we introduced into the crystal lattice. This process of introducing impurities into a pure semiconductor is called doping. Now, when students hear the word impurity. They often think impurities are undesirable. In most of the engineering applications, impurities reduces the performance. For example, impurities in drinking water or impurities in pharmaceutical products, metals are generally unwanted. However, in semiconductor technology, impurities are intentionally introduced because they improves materials electrical properties. In fact, the entire electronic industry depends on the controlled impurities. Without doping, there would be no transistor, no integrated circuit, no smartphone, no computer, and there is no internet as well. No, nothing today. Now, let us understand how remarkable this process really is. Suppose you have a pure silicon crystal containing millions and millions of silicon atoms. You may think that adding a few impurity atoms would make little difference. But surprisingly, even one impurity atom among millions of silicon atoms can significantly increase the conductivity. This demonstrates how sensitive semiconductor materials are to the atomic scale or modifications. That is why semiconductor fabrication plants, often called fabs, maintains extremely clean environments. Even microscopic contaminations can alter device performance. That's why we should be very careful while handling the instruments like the electron microscopes, scanning electron microscope and transmission electron microscope. We should be very careful while handling those instruments. That contaminants will change the properties of the materials. Let us now understand the purpose of doping. Why do we add impurities? The answer is simple. We want to increase the number of charge carriers available in the conduction band. Remember that the electrical conductivity depends on two important factors, that is number of charge carriers and their mobility. In intrinsic semiconductors, the number of electrons and the number of holes are relatively small and equal. As a result, the conductivity remains limited. By introducing a carefully selected impurity atoms, we can dramatically increase the carrier concentration and therefore increase the conductivity. Now, depending on the type of impurity added, we can create two different kinds of extrinsic semiconductors, namely N-type semiconductors and P-type semiconductors. These two materials form the foundation of virtually all semiconductor devices. Let us briefly understand the difference between the N-type and P-type semiconductors. In N-type semiconductors, doping introduces addition of free electrons. That is, when we add a pentavalent impurity into the a pure semiconductor, the pentavalent impurity atom consists of 5 valency electrons in the outermost orbital. Out of these 5 valency electrons, 4 valency electrons will make covalence bond with 4 neighboring electrons from the neighboring silicon atoms. In N-type semiconductors, doping introduces the additional free electrons. Therefore, the electrons become the dominant charge carriers in extrinsic semiconductors. In p-type semiconductors, doping creates the additional holes because in p-type semiconductors we will introduce the trivalent impurity atoms where there are only 3 electrons in the outermost orbital. Those 3 electrons will make the bonding with the 3 neighboring atoms and one vacant position is still available. So the p-type semiconductor doping creates additional holes. Therefore, the holes become the dominant charge carriers in p-type semiconductors. So we will discuss both types of uh, charge carriers, both types of semiconductors in detail in the next few. Very much for your kind attention. We'll meet again in the next video. Thank you.